Hey, welcome back to Fat Mama Physics. In this video, we are going to apply the work-energy theorem, which is the work is equal to the change in an object's or system's kinetic energy. So let's get down to it. Fat Mama Physics is dragging a 12-kilogram crate of board games. Same question as before, but now we can see it in a new light. So here we have the mass, and it's being pulled across the floor with a rope. Oh, it's making some sort of angle with a force here of 530 newtons. The object starts from rest. Ooh, that's very useful. And after pulling 22 meters, the crate achieved a final speed of 29 meters per second. So that's our final speed there. Calculate the work done on the crate after it was pulled. So whenever you see the work done on the crate or on any object and it doesn't specify the force, that means you need to find the work done by the net forces acting on the object. You have the displacement, you need the net force, so that means we now need to draw a free body diagram. So a free body diagram, we have the force of tension, which is at an angle. We need to resolve that later into its components. We do have Fg, we have the normal force, and we also might have some sort of friction force. And if we just sneak peek at B, there's some energy loss due to friction forces. So I'm just going to put that in so that we know what we're talking about. And since this work done on the crate is the net force, we don't know whether or not there is a force of friction or not. We just have to assume that there could be. It doesn't mention this crate is accelerating up or down, so I'm going to assume it's only accelerating in that forward direction caused by the tension force, meaning that we need to resolve this tension force into its x and y components, which this one is force of tension force x, and then the vertical force of tension y. Since we're not going to care about the vertical forces with no acceleration in that direction, not even the F net, so let's go in here and just write down what Ftx is. It is it's adjacent to the 36-degree angle with the hypotenuse being Ft. We are going to write this as Ft times the cosine of 36 degrees because we're going to use that later. Okay, so we know that the F net here is going to be Ftx minus force of friction. And we don't have the force of friction, unfortunately. And we can't just assume it doesn't exist for us to go ahead and calculate F net to calculate the displacement. But we do know, based on our work-energy theorem, that the work done by the net force is also equal to the object's change in kinetic energy. So let's go down here and see what is change in kinetic energy. It's the object's final kinetic energy minus the object's initial kinetic energy. Kinetic energy is just 1/2 mv squared for whatever speed that is at that point. So then let's write that down. In fact, we do have a few values. We have the initial velocity is 0 because the box starts off at rest. So this value is actually 0. The final velocity is 29 meters per second. With a mass of 12 kilograms, we can go ahead and put that into our change in kinetic energy equation. And then putting all that into our calculator, we get 5046, which rounds up to 5.0, unfortunately, times 10 to the power of 3 joules. Or 5 kilojoules. Hey, wasn't that cool? We didn't even need to know what the friction force was to calculate for the work done. We just need to find the change in kinetic energy. Hey, that was easy. Next up, we have B, the energy lost by the crate due to friction forces. Ooh, okay, so that's pretty tricky here. But let's think about this a little bit. So if we think of this box here as our system and the work that is put in due to the tension force here, which I'll just write as a sub T, that's going to cause this box to accelerate forward. But at the same time, it's going to lose some of that energy due to friction. which I'm going to sub that as F. And whatever is the total out of this addition and subtracting this away from energy from my system is going to be whatever is left over in my system. And whatever is left over in my system is how much this box will be able to accelerate and going forward. And this change in kinetic energy is exactly the same as the work done on my object due to the net force. So if I use this diagram to kind of give an idea of how I can framework this, I know that if I take the work done by my tension force subtracted by the work done on friction forces, which is pretty much equivalent to my system losing this amount of energy, because they're both measured in joules, and we know that work is equivalent to change in energy. And this is going to give me whatever energy is left in my system to cause it to accelerate, or the change in kinetic energy. In other words, this is my work F due to F net. And we have work due to F net from our previous question, which we already calculated the change in kinetic energy. So that we have already. What we need to find is this one, the work done by friction forces causing our crate to lose that energy. So let's just rearrange this equation first so we have that on one side of the equation. So I'm going to move this over here, so that's adding the work done by friction forces and subtracting the W net, F net over. So moving that over to the other side by subtraction. We get the work done by friction forces, or the energy lost, is the work done by the tension forces minus our work done by F net. So let's write a few things down. We know the work done by tension forces is the force of tension times the displacement and times cosine theta, which is 36. This one I need the cosine because my tension force is applied at an angle. Only the horizontal component is going to do any useful work. And we know the WF net was found in our previous question. We can just subtract that. And now what we need is Ft and S. Ft we know is 530 newtons, and displacement is 22 meters. We can put that all in our calculator. We get 4387. And rounding off to 2 sig figs, we get 4,400 joules of energy lost. Oh, and quick thing here about the work here. And we didn't have to worry about putting in an extra negative sign because we considered the direction of energy flow already by this negative sign we have in this equation. So this is the energy lost. In fact, this is one way you can solve this problem. There's a longer, more convoluted way to solve this problem by figuring out exactly what F net is and using F net and the force of tension to go and find the force of friction, and using work is equal to force of friction times displacement to help you calculate the energy or the work done by the friction forces, which is longer. And if you want, you can try out that solution yourself, but I won't do it in this video because it will be very long. Okay, so this is an example of where the work-energy theorem can be applied. There is a second problem, which then you can try. It's also more straightforward. It is also a recap of a previous question I've used before. So let's just read the question first so you know what you're doing. Mikasa has a mast, goes wakeboarding on the ocean. The rope she makes a 90-degree angle relative to the horizontal. The tension of the rope is 680 newtons, and she experiences 330 newtons of combined drag forces. Okay, so you probably need to draw a free body diagram there. Over the course of 340 meters. You want to find the work done on Mikasa. Hint, hint, that's the work done by the net forces. And second question, you want her final speed, assuming she started from rest. Ooh, you like starting from rest. Okay, so here is a good time to pause the video for you to try this problem. And now it's my turn.
First, we need to draw a free body diagram of Mikasa. First, there is the force due to gravity acting on her. There's the force due to tension acting at a 90-degree angle. There is the normal force pointing upwards. We are going to assume that the wakeboarding and everything is going to be horizontal, parallel with horizontal. There's also the drag force acting on her as well. The force of tension we can resolve into its x and y components. In the x direction, we have Ft cosine 19 because it's adjacent to the 19-degree angle. The upwards, we don't really care about that much. So to find the work done on Mikasa, we can either use the change in kinetic energy or using F net times displacement. But since we don't have final or initial velocity, we are going to use F net times S instead. We have the S, we need to find the F net along the x direction. The acceleration y direction is 0, so just in the x direction we have Ftx minus the drag forces. So then we can then plug that into our work equation. So our F net is going to be Ft cosine 19 minus the drag force, make sure you bracket that, times the displacement. We don't need the cosine again because we've already considered the net force along the horizontal direction. So using the cosine 19 only for the tension force, not on the drag force, because that's already parallel with the horizontal. Putting all our values into our equation, this is what we get, rounding to 2 sig figs, that's 110,000 joules. Next up we have finding her final speed. Now we have the work done. We can write the change in kinetic energy, final minus initial, in which the initial is 0 because she starts off at rest. That part just cancels out completely, and we just have 1/2 mv squared to isolate for the velocity. We multiply both sides by 2, then divide by mass. Finally, we take the square root, which cancels with the square. We can then plug in our values, in which the work we found in the previous question, making sure we don't lose any significant digits. Her mass is 68 kilograms mentioned in the question. Putting in our calculator, we get 55.9, rounding up to 56 meters per second.
Okay, and here we have the solutions to this problem. Notice that in this case, you did not have the final or the initial velocity. You had to use the F net to find the work done on Mikasa instead, and use that to find her final speed in question B. So hopefully through these examples you've learned a few skills that can help you tackle problems on your own. I wish you good luck in the process. Thank you for watching this video. Fat Mama Physics signing out.